how fast you can negotiate a curve, will it depend on the mass or the weight of the vehicle?
No.
All right. Okay, you said no. A lot of people will say yes to that one, and all of a sudden then the question, for those of you guys who say yes to that question, if you think that the weight of the vehicle is going to matter in terms of how fast you can negotiate a curve, do you think that the lighter cars will be able to negotiate it at a higher speed than the heavier cars, or vice versa? All right, so we will find out. All right, so here's what I'm going to do. We're pretty much done with this week's lecture. For the rest of the lecture, I'm just going to finish this up and then record it and put it online, so you have to kind of watch it yourselves. All right, so what I want to do is want to do the lab, so I'm going to put you guys into groups and let you guys kind of work on the lab stuff. But while I'm doing that, here's what I want you to do. All right, guys, what's the main cause of this accident as far as you guys are concerned? Let's have a discussion regarding that. What do you think is causing the accident?
Trying to accelerate through the curve.
Trying to accelerate through the curve. Okay. Okay, let me put it this way. Who would you blame? Do you blame the city or do you blame the drivers? Their fault here for these accidents.
I'd say the driver.
Yeah,
you can always, drivers are always their fault, but if I were to get into an accident like this, I would try to recoup some of my expenses. I would definitely go after the city. All right, this road design is atrocious. It's atrocious. Okay. The reason why I'm saying that is, all right, so whatever the speed limit is, it's probably 35 miles per hour on the right side of the road. If it's just 35 miles per hour, which means that you should be able to negotiate around 45 miles per hour. Yeah, you're on ramps, off ramps, it's always, what is it, 45 miles per hour usually? I mean, I can negotiate it at 50, 55, 60, 65. I wouldn't go up to 65, but you should be able to negotiate it up to 70, 75 miles per hour in reality. Okay, so they put those speed limits up there. But in reality, the speed limit is going to go down depending upon the weather conditions. If it's raining, it goes down. If it's snowing, it's going to go down. If it's icy, it's going to go down. So they put those speed limits on the side just to make sure that you remain close to it. You will not get a ticket if you're going at 60 and 45 mile per hour. The ramp, guys, those are just the warning speed limits. All right, so I bet you that there's a speed limit that's 35 miles per hour. This guy's probably going 40. This guy's thinking, okay, I just saw 35 miles per hour, and he wants to go maybe about 45 to 50 miles per hour. All of a sudden, the car just goes in a skid, so which means that static frictional force is maximized. All right. So my guess is more than likely the posted speed limit is actually way too close to the actual speed limit. Now, how did they figure out what the proper speed limit is? And how did they figure out what the proper speed limit is, given the fact that not all vehicles weigh the same? All right, so that's one of the things that we will investigate. And aside from that, the other question is, what is it that they could have done to fix this problem? Okay, obviously these accidents happening time and time again. So how do you prevent these accidents from happening? What do you guys think? Oh, I need to go to assignments.
They could start by at least posting a lower speed limit through there.
Okay, yeah, that's okay. And then the enforcement is going to be a problem. I think the speed limit probably just goes down a little bit too fast. Maybe just absolutely you have to kind of lower the speed limit to 25 or something. And then how do you enforce that? In case people don't take it seriously. Conceptual lecture lab.
I guess you'd have to post police officers in that case.
Okay, no, you don't want to do that because you want those people to fight real crime. All right, so what else?
Cameras.
Okay, we got the cameras. So the cameras are there to capture what's going on. Okay, it's not preventing anything. What else?
But we already have a camera that's not working.
Yeah, I mean it's working in a sense that it's capturing the fact that these guys are speeding. Okay, what else? What else can you think of?
Tickets.
Okay, well these guys, of course, they're getting tickets as well. So it's not preventing anyone from actually engaging in this sort of behavior. So what else can you guys think of?
Stoplights or stop signs.
Oh, cute. Yes, you guys have 5 points. That definitely would have helped. That would have helped. I would have put a stop sign in front of it, so you have to stop. Stoplight, maybe, well, stoplights is probably not going to make that much of a difference. Or you can make sure that everyone is merging to a single lane, so that's going to slow the traffic. What else? Speed bump. Absolutely. I would lower it and put a couple of speed bumps in front of it. That city did not do. What else? You can use, for asphalt, you could use higher coefficient material, higher traction numbers, okay? So that these things are not skidding or sliding down easily. Okay, so what else can you think of? How about banking it? Can you actually bank this? All right, banking is going to be a problem because it's an underpass. All right, so they won't be able to bank that. So it's kind of out of the question. Could have done quite a few. Obviously, they put enough lights. Every single solution that I gave you, with the exception of stop signs, would have cost city money. And the cheapest solution that they were able to come up with is literally just put up the cameras. All right, so if there's an accident, if I'm the driver, if I think that the city is at fault because it's a bad road design, which it is, there's no question about it. And then when you show up with your attorney, they will just play this video, and then a picture is worth 1,000 words. And test number 4, the conceptual evidently is partially graded. So just ignore your grades on that one for now. Okay, how do we know that the force of gravity extends all the way out to the moon, guys? All right, just feel free to answer the questions right now for extra credit. All right, so there are 2 ways we know that the gravity extends all the way out to the moon, right? All right, so one way is if it didn't, this one is partially correct. What would happen? The moon would have gone in a straight line at a constant speed. All right, that only proves that there's a force acting on the moon. It doesn't mean that the force acting on the moon is gravity. It just means there's a force acting on the moon, changing direction. All right, so how do we know that the force acting on it is coming from the Earth itself? It's circular motion, which means that it's accelerating, right, towards the center of the circle. That implies that there's a force acting on it. All right, so the force acting on it will be in the same direction. All right, so the force is coming from the Earth, so the assumption is it's gravity. It's an assumption. Assumption, it's the same force that pulls the apple down. We know for a fact that the force that pulls the apple down is gravity, because what happens to the apple? The apple is going to accelerate. Acceleration is g, and then what causes the acceleration is a force acting on it, directed towards the center of the Earth. So here's the force that pulls the apple down. So assumption is, given the fact that the forces are directed towards the center of the Earth, the force that pulls the apple down is the same force extending all the way out to the moon. All right, so that's an assumption. All right, so question number 2, suppose that the gravitational force by the Earth on the moon magically has suddenly shut off. It's shut off. How would the moon behave after that time? All right, so if the force of gravity vanishes, what happens to the moon? Straight line.
Speed on a straight line.
Very good. Give yourself 5 points. Straight line at a constant speed. All right, so the next question, how's the force of gravity related to the product of the masses? All right, so the force of gravity is related to the product of the masses directly, right? Small mass to big mass. All right, they will be attracted to each other through the force of gravity. So you have this direct proportionality. All right, so the force is directly proportional to the product of the masses. All right, so how's the force of gravity related to the distance between the masses? All right, so the distance is going to be measured with respect to the center of mass. Force is going to be inversely proportional to the distance, which means that the force is going to diminish with distance as the square of the distance. So we got this inverse relationship. Larger the distance is, smaller the force becomes. So as you increase the distance, as the separation distance increases between the centers of mass, force is going to diminish, and vice versa. As the masses get closer together, become closer together, the force is going to increase inversely as the square of the distance. All right, so what's the gravitational constant? What is that? Gravitational constant is it denotes the strength of gravity. It's a small number. You will have 10 zeros before you hit the first number. It just tells you about the strength of gravity. That's it. All right, so why is G constant? That's the same as saying, why is it that everything falls at the same rate under the influence of gravity? G is constant because how fast objects fall is going to depend on 2 things. It's going to depend on the mass of the planet. All right, so it depends on the mass of the planet. It's also going to depend on the size of the planet, or a star, or anything for that matter. All right, so it's going to depend on the radial size, the radius of it. Okay, that's what it means. So how fast objects fall only depends on the mass of the planet. It's going to depend on the mass of the planet. It's going to be inversely proportional to the square of the size of the planet. All right, so the mass of the planet is constant. This is constant. Size is constant. As a result, G is constant. Okay. This one is kind of tricky, because if you were to answer it this way, you may end up actually losing a point for something like that. You'll probably lose half a point for something like that. And there's a good reason for it. My question is going to be on the test. Why is it that the mass of the following object does not matter? Why is the mass of the following object does not matter? The reason why the mass of the falling object does not matter is because it gets canceled out of the equation. You can answer it that way. Once again, you're not going to get full credit for it. Guys, this equation tells you that the mass of the falling object doesn't matter because the mass of the falling object does not make it to the final equation. Obviously, this got canceled out somewhere. Then again, we knew that the mass of the falling object did not matter before we did the algebra. Algebra says the same thing. It says, hey, listen, the mass of the falling object doesn't matter because the mass gets canceled out. This leaves us with the same question. The question is, how come the mass of the falling object doesn't matter? I mean, everything falls at the same rate. The question was why? Why is it that everything falls at the same rate? So we still have the same question. The question hasn't changed, except the question is not answered. Okay, I was hoping that we were able to answer the question, and then we looked at Newton, and Newton goes, okay, so the weight is caused by the force of gravity, blah, blah, blah. Eventually, the mass cancels out, and then this is what we got left with. It's the same question. Why is it that the mass of the falling object does not matter? I mean, just imagine a guy who was taking physics as a freshman 40 years ago, and this is